Hey everybody, this is Professor Serge. Welcome to the lesson on the derivation of the volume of solids without calculus. Now the reason I'm deriving these volumes without calculus is twofold. First of all, I think that the techniques I'm going to show you, they're going to help you understand fundamentally the math that's involved. See, I've been studying math for over 15 years, and even I don't remember most of these geometric formulas. So what's the point in me just giving you the formulas so you can plug in the values if I don't expect you to ever remember them? Now the other reason is that I'm hoping to interest at least a few people who don't know anything about calculus to try and learn it. You see, a lot of the ideas I'm going to show you here are very similar to the calculus equivalent. In fact, one of the first things that you start to get taught when you learn calculus is how to calculate the volume of shapes, just like this. So I'm hoping this is going to be kind of a bridge for people who are just on the verge of getting into calculus. So we're going to start with a very simple shape that everyone should already know how to calculate the area of, and that's the square. Now the area of the square, as you should recall, is W times H. Now the reason that I'm bringing this up is I want you to try to visualize what W times H means. The way we could think of it is you have this line segment here, W, and you want to visualize this line segment moving towards the other end of the shape, the other end of the square. It's going to be sweeping out an area, and it's going to be following the path of H. So this line moves across inch by inch until it reaches the end, and it's going to pass through every piece of the square. That's effectively what we mean when we say W times H is equal to the area. All right, now I'm going to show you how you can use the same way of thinking now for 3D shapes. So I'm going to draw the cube version. Imagine we already know the area of the top. It's going to be width times depth, and we know the height. So this now two-dimensional shape is going to trace along. It's going to follow the path along H. It's going to follow this path, which is a distance of H, and it's going to actually pass through every piece of the shape, every piece of the 3D cube, all the way to the bottom. And effectively, what you're doing is you're saying the volume is the top shape, the top surface, W times D, and then passing that through to the bottom, you're multiplying it by H, so your volume is equal to width times depth times height. Now if you think of a shape this way, a cylinder is not very much different than a cube. It's got a top face, only the top face has a different area. Instead of width times depth, it's going to be area is equal to the area of a circle, which is pi r squared. Now I want you to visualize the same event happening, that we're going to take this area, the top face, and project it downwards along H, all the way to the bottom of the 3D shape, and it's going to fill in the entire volume. So that's equivalent to multiplying the top face by the height, the path that it travels. So then the volume of the cylinder, is equal to pi r squared times H, or the area of a circle times the path that the area of the circle is traveling. Now I'm going to show you an additional technique for calculating the exact same volume, the exact same formula. Now what I need you to imagine is we have a knife, and it slices our cylinder right through the top, and the knife passes through all the way to the bottom. So we're creating a cross section right here. It's a square, it's a rectangle. And one side of the rectangle passes through the center line of the cylinder. Now if you imagine this rectangle rotating around the center line, it's going to sweep out a volume. See, it's going to pass through the entire cylinder at all points in the volume, and that's going to be the volume of our cylinder. Except this time, the path that we're taking, see, if you remember in the previous step, we had our top face, and it went from the top of the cylinder to the bottom, following the path H. Now we're going to actually be following the path, which is the circumference of the top circle. See, it's going to rotate around through the circumference. This point, you visualize this point on the corner, is going to travel all the way around 360 degrees to the other side. So we're going to use the same exact approach as before. we take the area of the surface that we're rotating, which is going to be area equals height times radius. You see the height here is defined, and here's the radius of the top of our cross-section. So it's going to be height times radius times the path. In this case, the path is 2 pi r. Now actually, we're not going to be using the radius of the outside of the circumference. We're not going to be using that exact radius, and I'll explain why. Well, so I said we're rotating this cross-section around the center line to create a volume. Well, this cross-section has a lot of points. There's a point here, there's a point here, there's a point here. Why should we use the radius at the edge when there are all these other points to choose from? So what I'm going to show you here is if we think about a top view, I'm drawing the same shape from the top. We have our cutout right here. And if you imagine that cutout rotating just a little bit, it's going to create a pie, a little piece of a pie, like this. Now, if we choose the radius on the outside, you could see how much volume we're sweeping. It's more than the volume on the inside. So if we use a radius on the outside, we're going to be overcompensating the volume. See how much volume this is sweeping out? If I use the radius on the inside, which is 0, I'm going to be undercompensating. See how little volume is being swept out compared to here. It turns out that the appropriate radius to choose is in the centroid. In this case, it's right in the center because it's a square. See that right here? If we use the centroid as the point of revolution, it's kind of going to average out the volume so that we get the right amount. We're not going to overcompensate or undercompensate. Now this is called Pappus's theorem. This was developed about 1400 years before calculus. The idea that we can rotate this cross-section to get the volume of the cylinder. But it's very similar to calculus, so it's kind of amazing that it was developed so early on. So what is the centroid here of the square? Well, it's half of the radius. It's right in the middle. So instead of rotating it about the path produced by r, the circumference of the circle about at r, we're going to be rotating through the centroid, which is r over 2. This is r over 2, where this would be r. So let me erase that r, put r over 2. That's equal to the volume of a cylinder. And we just have to do a little math here, a little algebra, and we'll see that we have pi r squared h equals the volume of a cylinder. See the 2's cancel out. We have 2 r's, pi h. That's the same formula as I just derived using the other method. And now we're going to derive the formula for the volume of a cone. And we're going to use the technique very similar to what we just did for the cylinder. If you remember, we used 2 techniques for the cylinder. The first technique was we took the base of the cylinder, the area of the circle, and we projected that upward a distance h. So we multiplied the area by h. Now that's not going to work here. And the reason it's not going to work here is because if we imagine this area projected upwards, that creates a cylinder. A cone has a different circle at each individual height. See, if you took this circle and projected it upward a little, you would have to shrink its circumference. And that's not going to work with this technique. We're going to have to introduce some calculus to do that, and that's really not the subject of this lesson. So we're going to use the second technique that I showed you. And that is we think about a center line that goes through our cone and a cross section that's adjacent to that center line. In this case, it's going to be a triangle, not a square. So our objective is to take this cross section and rotate it about the center line so that it sweeps out the entire volume of the cone, and that's going to give us V. That's going to give us the formula for the volume of the cone. Now, just like in the previous cylinder example, first thing we need to do is figure out the centroid of this triangle. Now, it's not as easy as getting the centroid of the square. In the square, I just told you it was the middle, and so it was r over 2. Remember, this distance here is r, so the center would just be r over 2. That's not the case for the triangle. to calculate the centroid, we're going to do it a little bit more formally. And so I'm going to draw out a graph here, and we'll just say this is x and y. So along the x-axis, that's the distance that we're interested for the centroid. The centroid is going to be somewhere here. I can just tell you right now, it's going to be about here. But we're only interested in the distance along the x-axis, and that's because we're trying to figure out the distance r from our center line, and the distance r from the center line is going to be perpendicular to the center line, which is going to be the x-axis. All right, so the way we do that is we take the coordinates for the three vertices, 1, 2, 3 vertices. This coordinate's going to be 0, h, this coordinate's 0, 0, and this coordinate would be r, 0. So having those three coordinates, if we average the x-coordinate, that's going to give us the x center of area. If we were to average the y-coordinate, that would give us the y center of area. All right, so I'll just get both real quick here. So if we add up all the x components, we get r plus 0 plus 0, and divide that by 3 points, gives us the average equals r over 3. Or in other words, 1/3 r. If I wanted to get the y component, so that I'll call this x centroid. If I wanted to get the y centroid, that would be the sum of the y components, h plus 0 plus 0, averaged, which means divide by the number of points, and that's going to give us h over 3, or in other words, 1/3 h. So this centroid right here has an x and a y component. And the x component, as I pointed out, is what we're interested in, and that's 1/3 r, because 1/3 r is the average of the x components. So that's approximately here. So what we're going to do now is we're going to take the area of this triangle. If you remember, the area of a triangle is equal to 1/2 base times height, or in our case, it's going to be r is the base and height is h, so 1/2 RH, that's area of the triangle. We're going to rotate that along the path at this radius. So the radius is 1/3 r, and we're going to go along this path. And this path is the circumference of the circle here. All right, so we're going to say that the path equals 2 pi times r. The radius of the path is actually 1/3 r, and that's the path. Now if we multiply these two together, if we multiply the area by the path, that's going to give us the volume. So let's try that. The volume of the cone is equal to the area of the triangle, 1/2 RH, times the path that we're going to travel. It's going to be 2 pi over 3 r. And now it's just a matter of doing the algebra. Cancel out the 2's, and you get volume is equal to 1/3 pi r squared h, which is the volume of the cone. And that's all there is to it. So I'm hoping at least one of you learned something. And if you have any questions or comments, feel free to leave them below. Or if you have any ideas for any additional videos that you want to see, go ahead and leave those below, and hopefully I'll have time and I'll make them. All right, bye.